What's up, everyone? Welcome back. My name is Hako, and welcome to the second video of data engineering in advanced SQL. Thank you. If you watched the first video, SQL Foundations, this will be the continue of the more advanced level. So in the first video, we covered select, joins, group by, CTEs. Those are building blocks. Today, we're covering the SQL that you will actually use in the daily life work as a data engineering. So this is the basics, just core concepts. We're going to cover window functions, recursive queries, pivoting, optimizations, much more. So yeah, I will be uploading the link down below. So it's the community free for all. So you can practice hands-on exercises. This just covers the core concepts. And if you like it, please like, subscribe. If you have any feedback, please comment. I will be very happy because I'm just starting this series. We're going to be covering data engineering, machine learning, and AI. So it's going to be a fun journey. So stay with me. And without any further ado, let's jump right in. Okay, we're going to start with Windows functions versus group by that we already covered. So here's the problem. You have students and scores, and you want the average per subject. Group by does that, but it crosses the rows. 4 students becomes 2 averages. The individual scores are gone. What if you want both? Each student scores and their subject average on the same row. That's what Windows functions do. Look at the diagram. Left side, group by funnels 4 rows into the 2 summaries. Right side, window functions keeps all 4 rows and adds the average as a new column. Same math. Here's the syntax. Select your columns, then average score over, and inside that over, you write partition by subject. Think of partition by as group by's cousin. It says, calculate this average separately for each subject, but without collapsing rows. Check the result. Alice has 90, Bob 85, Carol 78, and then 92. And right next to each score, the math average 87.5 on every row. The original data is intact. That's the magic of window functions. Now ranking. SQL gives you 3 functions that handle styles differently. Look at the results table. Carol has 92. She's first everywhere. But Alice and Bob are both tied at 85. Row number doesn't care. It just assigns 2 and 3 arbitrarily. Rank gives them both 2, but skips to 4 for them. Because positions 2 and 3 are taken, dense rank gives them both 2, and the next number is 3. It never skips. That difference matters when you're filtering, which brings us to the next slide. Okay, this is probably the most useful SQL pattern you'll learn. Your boss says, for example, give me the top 2 students per subject. You cannot use limit 2. That gives you top 2 overall, not per subject. So the trick, dense rank in a CTE to rank everyone within their subject. Then filter where rank is less than or equal to 2. Why dense rank and not rank? Because if 2 people tie at number 1, rank skips number 2. Your filter will miss a slot. Dense rank never skips. This pattern works for top products per category, latest orders per customer. You'll use it everywhere. What if you need to compare a row to the one before it? Like, you have daily stock prices and want to know if the price went up or down. Normally, you will need a self-join. Messy, right? So lag and lead make it simple. Lag looks at the previous row. Lead looks at the next one. Look at the timeline. We're in January 4th, the orange box. Pink arrow points back to January 3rd. Lag gives us yesterday's price, 187.1. Green arrow points forward to January 5th. Lead gives us tomorrow's price, 186.3. At the bottom, the price change. 184.5 minus 187.1 equals negative 2.6. One line of SQL, no self-join. Here's something that trips up everyone. Imagine you're looking through an actual window of your data. The frame of that window controls how many rows you can see. By default, the frame starts at the first row and ends wherever you are right now. So if you are in row 5, you can see rows 1 through 5. That's fine for the first value. Row 1 is always in view. So it always returns the very first price. But last value, it can only see up to your row. So on row 5, the last value it sees is row 5. Your own value, useless. The fix is in the highlighted lines. You tell SQL expand the windows to show the entire partition, first row to last. That's what rows between unbounded preceding and unbounded following does. Think of your bank account. Every transaction changes your balance. That balance is a running total. In SQL, you do this with sum and a frame clause. Rows between unbounded, preceding, and current row means add up everything from the first row to here. Check the result. January is 45K. The running total is 45K. February adds 48K, now 93K. March adds 45.5K. So that's 138.5K. Each row carries the full history. Quick tip, swap sum for max and you get a running maximum. Great for tracking peak revenue. Every manager asks, how are we doing compared to last year? Lag makes it easy. Normally lag looks one row back, but you can give it an offset. Lag with 12 looks 12 rows back. If your data is monthly, 12 rows back is the same month last year, right? Look at the diagram. Each orange arrow connects January 2024 back to January 2023. Subtract and you get the growth. 51K minus 45K equals plus 6K. Important caveat. This only works if your data has exactly one row per month with no gaps. Missing months means the offset lands on the ground row. You know the basic CTEs, right? With something as, then your query. Now we're chaining them like an assembly line. Each CTE does one job and passes the result forward. Look at the diagram. We start with 10 employees. First CTE calculates average salary per department. Second CTE joins those averages back and checks who earns above average. The result? Just repeat. Each CTE did one clear thing. And you can test each one independently. Way better than cramming everything into one giant nested subquery. Let's see a powerful example of this. Here's a perfect example of CTEs in action. Remember the top end pattern from earlier? We said you cannot filter on a window function directly in a where clause. SQL won't let you. But if you wrap it in a CTE, you can. Look, the CTE ranks everyone by salary within their department. Then the outer query just says, give me rank 1. That's it. Sarah is the highest paid in executive, Tom in engineering, Lisa in sales. This pattern, CTE for the calculations, outer query for the filter, is something you'll use over and over. Now the wildest CTE trick, make it call itself. Look at the diagram. It starts with Sarah, with CEO at level 1. And it finds everyone who reports to Sarah, Tom and Lisa at level 2. Then everyone who reports to them, Mark, Amy, Nina at level 3. It keeps going until there's nobody left to find. The result is a complete org tree built level by level. And see that path at the bottom? Sarah, arrow Tom, arrow Mark, arrow James, arrow Mike. The full chains from CEO to individual contributor. Let's see how to write this. Here's the code. With recursive, then the CTE name org tree. First part is the anchor. Select the CEO where manager ID is null. That's level 1. Then union all connects the recursive part. It joins employee to org tree itself, matching manager ID to ID. Each pass finds the next level down. The level counter goes up by 1 each time. SQL keeps running until no new rows are found. The result? Every employee with their level and full path from CEO. Your manager wants a spreadsheet with each salesperson revenue per quarter in columns. That's pivoting. Turning rows into columns. Look at the comparison. Left side, row data. 1 row per quarter per person. 4 rows just for Alice. Right side, Alice is 1 row. Each quarter is its own column. So the trick? Case when inside sum. You say, if this row is Q1, give me the revenue. Otherwise 0. Sum adds up only Q1 values per person. Repeat for Q2, Q3, Q4. Same data, different shape. Here's the full cross tab. Each sum case when block creates 1 column. Q1, Q2, Q3, Q4, same pattern, just swapping the quarter name. The total column at the end is a plain sum. No case, adds everything. The result, Alex Rivera leads with 242K, Bob Chen with 226K, Carol Davis at 210K, sorted by total descending. And you can pivot on any categorical column, not just quarters. In the exercises, you pivot by product line, software, hardware, services, same case when trick, different values. Set operations combine or compare entire result sets. Think Venn diagram operations. Look, customers 2023 on the left, 2024 on the right. 5 people appear in both circles. Those are retained. Left only, like Alice Johnson and Bob Martinez, churn. They left. Right only, like Karen White and Liu Sang, new customers. Union gives you everyone deduplicated. Union all keeps duplicates. Intersect gives you only the overlap. And except gives you one side minus the other. 2023 except 2024 equals churn customers. Now, look at how you combine all three in one query. The code has 3 sections, each starting with a comment. First section at the top, customers 2024 except customers 2023. That gives you people who are in 2024 but not in 2023. New customers, each one gets labeled new as a status. Second section in the middle, flip it. Customers 2023 except customer 2024. People in 2023 but not in 2024, that's churn. Third section at the bottom, intersects, gives you people in both years, retain. Union all gives all 3 sections together into one result. One query, complete customer movement report. Last topic, making your SQL fast. Look at the left side. See that where clause inside the subquery? It says OI.order ID equals H.ID. That H.ID comes from the outer query. That's what makes it correlated. The inner query depends on the outer query. So what happens? For each row in order headers, SQL has to run the entire subquery from scratch. 1 million orders, 1 million subqueries executions. Now look at the right side. Same result, but join plus group by. It joins once, group once, done, right? One pass through the data instead of 1 million. The difference, second versus minutes. So it's efficient.